Yeah. So we learn about following things, that if there is a pole in a system, it's going to contribute minus 20 dB per decade, or it's equivalent to minus 6 dB per octave. 0 is going to give you plus 20 dB per decade. It's equivalent to plus 6 dB per octave. And if your transfer function starts with k by s, then you should go to 20 log k, and thereafter it keeps on decreasing, and thereafter you are adding other things also. If it is k times s, you have to go to the frequency, which is equivalent to 1 by k, and you have to draw plus 20 dB per decade, and thereafter you have to add other frequencies. And if you have something like this, k divided by s plus x, then it's so 20 log k. Depending on the value of k, it might be on upper half of 0 dB or lower half of the 0 dB, and this is going to give you minus 20 dB per decade. This is also minus 20 dB per decade, and this is plus 20 dB per decade, right? This is what we learn in terms of magnitude, right? Generally we study everything uh, in feedback. So this is just a quick review on like again the operational amplifier, just for teach you what is happening in feedback. Okay, so this is not part of the course. I am not going to ask anything from here. Okay, just for the repetition. But if you haven't understand, have you understand this part? Just let me know. If you don't know, then I'll talk about that also. Okay, I should make it, because do you know the answer? How did you do that? How did you get this answer? You have mugged up, or you know how to do it? So you, no side. This side is no, no. Okay, because like India, some people are calling yes like this also. That's why I'm asking. No. So okay, how many doesn't know? Do not feel shy. Okay, two, three. Okay, so let's follow. I'm going to derive it. You have to remember only two things. It's very easy. It's ultra easy. It's not difficult, by the way. Yeah, Swarna and Vaishali. It's easy. You are talking something. Okay. So there are two golden rules we are going to follow. Manas and Rishabh or Ritik. No. What's your name? Dhruv. Yeah, Dhruv and Manas. Two rules: V plus equal to V minus, and current will not flow inside the op amp. Okay. This is only possible when we are having following star mark conditions, which we are not generally bother about, but we need to know that those conditions are: the gain of this amplifier is infinity. Okay, actually third one is also there. You are not going to go beyond plus V supply and minus V supply. This is a limiting thing, right? A is infinity. One more thing, I like to make this amplifier as a voltage control voltage source, because input is voltage, output is also voltage. If these two things are already known to you, then your input impedance has to be infinity and output impedance has to be zero. So this is also one of the condition to make sure that this is ideal voltage control voltage source, right? So these two are the star conditions. Just keep it in your mind. But so with that, we have to follow these two golden rules. This is already known to you. So generally these two are known as the golden rules, right? Kathy, you know, right? Kathy? Kathy, okay. So, okay. So let's follow these two rules. So what these rules are saying. So V plus equal to V minus. So this is V plus terminal and this is V minus terminal. Minus. So what is V plus terminal right now in terms of voltage? 0 volt. So as per this rule, V minus is also equal to 0 volt. Now there is an input. This current is flowing this way. So that current will not go inside, right? As per the second rule, Dhruv. So this current will go outside, and this potential is V out. Now we are writing the KVL, right? KVL is part of this course. So I believe you know KVL. So can you write down for the first current? Let's call it I1 and let's call this one as I2. What is I1 equal to? V in by R1. Okay, so V in minus 0 by R1. And what is I2? 0 minus V out divided by RF. So it is going to give you minus V out by RF. You can also see that I1 equal to I2. If I1 equal to I2, then can you tell me what is V out by V in? Manas and Dhruv. Minus RF by R1. Right? So now there is no problem, right? Now you know the answer. This kind of amplifier is known as inverting amplifier. The only reason for calling this is this has two terminals. One is called inverting terminal. This terminal name is inverting terminal, and this terminal name is non-inverting. So if you are connecting the input at inverting, it's inverting amplifier. If you are connecting this to non-inverting, means like reverse way. But remember, we need to keep things in negative feedback. Still we are talking about negative feedback. We are not talking about the positive feedback till now. You understand that this is plus and minus. Now I am connecting same topology, but the only difference is V in is here, and this is RF, this is R1, right? Still it's negative feedback. Look at this. This is negative feedback, but the input is given to non-inverting amplifier. That's why the name of this amplifier is non-inverting amplifier, right? Still it's like negative feedback because the output is not written here, but it's positive. Okay, so positive is coming back to minus, so it's a negative feedback, which is the important thing, because negative feedback will make sure that your system will be stable. And you know what is the stable means. There is no oscillations at the output. Okay, so now very quickly, can you tell me, Manas and Dhruv, can you do it in your notebook and tell me what is V out by V in? So all the competitive exam, if you are going to give like IES or maybe GATE or other exams, op-amp is the like it's a part of the question paper where you need to score, right? You cannot say that I don't know, right? Like almost like 10 marks out of 150 of GATE examination is op-amp, and the questions are toy questions. Believe me, right? Even whole op-amp is toy, right? There is nothing difficult. Are you following, right? Okay. So that is a problem. If I shift my chair this way, then I can see only this side. Okay. 1 plus RF by R1. Did you find any difficulty, Manas, Dhruv, and whoever doesn't know? Okay. But okay, one more question I'm asking. It might this for all. What is the output if this is V in? Hmm? So if it is V in, I could have done this one also. Let's keep one wire. right? If I connect that wire, V out equal to V. Why to use this whole triangle? Buffer. Okay. So everybody know about buffer? What is buffer? Rohit, do you know? Okay. Okay. So those who talked about buffer, so can you like elaborate why, like what is the role of buffer and why we are doing such thing? You are right. This is buffer. I'm telling you because this is going to be used in your design practicum. Hello. So any Piyush, you told right? This is buffer. So okay. Now let's assume that I have a circuit like this. Okay. Whose output is connected to 1 volt, right? This is 1 volt. I'm taking output with some input impedance, sorry, output impedance of this black box. It is giving me 1 volt. But when I am going to connect it to a circuit, because I should teach that way or not. So there is another circuit whose input impedance is, let's assume that it's 50 ohm. Okay, input impedance is 50 ohm. So let's forget about this side and that side. This side is 1 volt. Whenever I am going to connect it, let's assume that I am going to connect it via one probe which is 50, and this side is also 50. So this circuit effectively get how much voltage? 0.5 voltage. This is called the loading effect because this circuit is not able to drive the next part. This is going to happen in the case like whenever your circuit is bigger, like the resistance of this square and this square, which square will have the higher resistance? Second one? No, because of rho L by A, as per area, this resistance will be actually smaller, and to drive a bigger speaker is difficult than a smaller speaker, right? If you are connecting your earphone, it will work, but if you are connecting a big, some 1000 watt of or maybe some more power hungry speakers, then it will not be going to work because they will have some resistance which is very small, and small resistance cannot be uh, actually driven by the previous circuit. That's the problem. If it is higher, no problem, right? You can see that instead of 50 ohm, if this is lower resistance, higher resistance, no problem, right? And that is what the characteristic of voltage controlled voltage source. So here what you are doing, you are connecting voltage controlled voltage source with, not with voltage controlled voltage source, but you are connecting with some circuit which is current control, whose input is current. It's asking for current, not for voltage. But if you want to do that, the voltage to current, or if you want something where these two circuits are not going to talk to each other, I want that just voltage should go there, not current. In that case, if I do this thing, will it work? Because it has only two golden rules. One says V plus equal to V minus, and there is no current flowing inside op amp, right? So there is no current. This circuit is also known as driver circuit. It's much more complicated than what I have drawn. This is just crude way to start with. Okay, because how much current do you need? It's required by the um, output power of this op amp, right? If you need some amperes of current, it cannot drive it. Our 741 cannot do that. It has the power capacity of 1 milliampere. That's it. So you need to read that. But if you are connecting this to a motor, this motor guy will directly tell you, take this driver circuit or driver chip, which is going to give me the sufficient current, right? You have done something like this. You are trying to drive the motor, but you are keeping something in between. That is the driver circuit or the buffer circuit. Yeah. If you haven't done it, you are going to do it in design practicum. You need lots of motors. It's not actually, DP is not just electronics, it's a you can say mechatronics, right? It's a robotics things where it's a mechanical plus electrical. So all the things which are mechanically very big, you cannot drive them. If it is small, you can drive it. If, so such things you are going to need it. Just to appreciate that, I kept it here, that these things are very important. Are you following this, right? Now the usage. Now the next question is, so we learn one way of solving the op amp. Op amp will work in the negative feedback and follow the two golden rule only when it's in negative feedback. This was also one of the star condition which we haven't told at the beginning, right? If it is in not in negative feedback, it will not follow this condition. It will follow something else. But let's assume that you are not in negative feedback nor in positive feedback, but you are keeping your operational amplifier in open loop. If this is plus, this is minus, and let's assume that A equal to infinity. This is plus V supply and this is minus V supply. If I am giving here 1 volt, if I am giving here 2 volt, what will be the output in your opinion? Have you studied this? Okay. This is another class of using op amp, but it's in open loop. It's not connected anywhere. It's open loop. Open loop is unstable system. If you remember, I told you either it will reach plus V supply or minus V supply. So what exactly this circuit does, V plus minus V minus multiply by gain, that will be your output. So okay, you can do that. V plus is 1 minus 2 multiply by infinity. So what is the output? Minus 30, because you cannot go beyond that, right? So it's restricted to minus 30. And similarly, you can find out like other way around also, you will get it plus 30. If you are doing this, which is going from minus 30 to plus 30, and if I make this one 0, let's not make it 30, but let's make something else, right? I'm giving here some sine wave. So what will be the output? Around 0 volt there is a sine wave. So what will be the output? So right or wrong? Plus 30 and minus 30, right? This is called sine wave to square wave converter, and this has also one name. It's called zero crossing detector, right? It's a zero crossing detector. It detects this value. Whenever it goes above that value, output is plus 30, and we are going to declare this one as digital logic 1. And this is the simplest ADC, which is 1 bit. Right? This is just simple way to realize analog to digital signal, and then you can do whatever you want. There are other algorithms are also working afterwards, but this is one way, right? So are you following this? This kind of open loop configuration is known as comparator. The name of this configuration of op amp is known as comparator. Okay. Yeah, so two values are comparing, right? So if V plus is higher than V minus, output is digital logic 1. Let's say in talking in terms of digital, V plus is lower than V minus, the output is digital logic 0, right? So it compares two value. Generally when you want to compare, or if I want to say that the temperature is very high or low, let's assume that I want to find out the temperature is very high or low, that temperature needs to be converted to some voltage, right? And that temperature, let's assume that I am calling 40 degree is equal to high, and equivalent to 40 degree, there is some voltage I created, and that voltage is, let's say, 2.3 volt, and I am connecting here the sensor, temperature sensor, which is continuously giving me some value, and it checks whether it goes high or low, and it records digital logic 1 and 0. If it is high, digital logic 1; low, digital logic 0. Right? Okay, no problem, right? Till now, any problem? Then I can talk about the third one. Okay, because you told me yesterday you haven't studied that. This is also very important. It's known as, okay, rather than writing the name, let's write it down. Positive feedback. So the output of this one is not same as the previous one. It's not same. Right now you need to look at that. The positive is here connected to the output, means it's a positive feedback. So in the case of positive feedback, we need to understand one thing, that we are going to use golden rule but in a different way. So because of like lower amount of time, I am just giving you the derivation, direct answer, not derivation. So v out, v in versus v out looks like this one, and known as hysteresis. You know about this, right? Which remembers the previous thing, and the path when you are moving from, let's say, from this side to this side, if it takes this path, when it comes back, maybe it takes another path, right? And this side it's minus v supply, and this side it's plus v supply, and there are 2 points. So if my v in is, let's call this one as vt n, and let's call this one as vtp, p for positive, n for negative, and t for threshold, threshold voltage positive side and negative side. So let's assume that I have started traveling from this side. So my v in is actually some value which is somewhere like, if I am going from this side, if my v in is any value minus infinity to plus infinity, or so minus infinity to this point, output is always plus v sub, right? Means maybe some value plus 30 or minus 30, it doesn't matter to us right now. So if my input is from minus side to vtp, oh sorry, vtn, the output is nothing but plus v supply. And if it is from minus v sub to vtn, output is again minus v sub, right? Input, just look at this x-axis, I'm moving the x-axis, and what is happening at the y-axis? The only change happens when you are here, or if you are moving in different path, change happen when you are here. Otherwise output is either plus v sub and minus v sub. We need to find out just this threshold points. So if I want to find out this, means when v in is equal to vtn, and maybe one case when v in is equal to vtp. Yeah. So at this point, what is happening? So now I'm saying that you are going to use the golden rule, means v plus equal to v minus, and current will not flow inside. These two rule you will follow only at these points, only at these points, not other points. So for that you already know that v out by v in is equal to minus rf by r1. This minus rf by r1 is not happening because of this plus and minus terminal, by the way. You can see that, right? Because v plus equal to v minus, so this is 0 volt, and you are going to flow two currents, I1 and I2 are equal, so it's v in minus 0 divided by r1 is equal to 0 minus v out divided by rf. That will give you minus rf by r1. It doesn't matter what thing you are connecting here, but the answer will be same. Now you already know that you are interested in finding out v in, right? So it depends, you are traveling from this side or you are traveling from this side. So for the case of vtn, you are traveling from here, when v out is nothing but plus v sub. If you replace that, when v out is equal to plus v sub and this is vtn, it's equal to minus rf by r1. So vtn is nothing but minus rf by r1 times v sub. So you can see that now the term becomes negative and it's at the negative side. So you can find out this threshold, and similarly you can find out this threshold also, which is rf by r1 times v sub.
So for minus infinity to t, what is that in green? TP.
Yeah, tp.
So there, green.
This side, okay, huh? So if I am traveling from minus v sub to plus v sub in a reverse direction, then this is going to happen. So I found out two threshold point when it has to change, right? So the output is, so I can show you what is going to happen and what exactly this circuit does. Circuit will give you output as 1 and 0 only. Let's assume that this is my input. There are 2 points which I have found out, VTN and VTP. I marked them on the sine wave, which was the input. And when it's above this, the output is 1. If it is below this, output is 0. In between, there is a slope. So output is always oscillating, right?
In digital, how we read this?
In digital, it's again 1 and 0. The noise margin is. Yeah. You must have experienced this, no? You haven't done this thing ever. If you zoom your clock, the clock is always like there's some slew. This is known as slew rate. That's the reality of all the square wave. You can never have this kind of square wave. Look, if my system is running at 2 gigahertz, 2 gigahertz, if you zoom it, you will find such kind of things. So as Amol is saying, this is a problematic, right? You are saying it's not good. You like only this point to this point, but that's not true. We like from this point to this point. Okay, let's go to, this is exact middle value, right? If you are here, you cannot identify whether my digital signal is 0 or 1, but you can identify with some margin. I'm saying that this is the point I am not able to tell you, but if you are above this, it's digital logic 1. This is known as noise margin high and this is called noise margin low. You studied? No. This is digital, plain digital. Okay. Somebody gave me one suggestion that you should tell me that I should float new course called digital electronics, just digital, for computer science and electronics. What do you say? New course I'll float as elective for third semester students. Maybe you will not get that advantage, but for third semester. What do you, yesterday, like one of the student told me this.
Different from DSD and CO.
No, it's plain digital. It's fundamentals of digital, starting with the Boolean algebra, go till the processor design. Right? A real digital thing, which you like this. Yeah, there is no course. Unfortunately, we don't have analog course. No course on digital also. So everything is in applied electronics. That's the bad part, right? So anyway, how is your DSD course is going on? How many have taken that course?
Only one lab.
Okay. So how is going on?
It's good.
Nice.
Link
Okay.
क्या already.
Himanshu, what do you think? FSM is important for DSD. FSM is very important. Okay. There is something called finite state machine. In SNTC we can have one lecture if you like. I can give that, or maybe Himanshu, can you give that lecture on FSM? Is it possible for our student SNTC? That will give them insight for digital things. That is very important. Without that, it's very difficult to study computer organization or DSD, in my opinion. Like, and if he has same, okay. And if you want to have it like it's a recording is already available, right? IC161, you go to my course, recording is already available. Okay, so that's all about this op amp. There is okay. Anyway, whichever way you like, it depending on value of RF and R1, depending on the dynamics of op amp. Thank you, you are right. Okay, it's not you who is choosing that way. First of all, it's chosen by the circuit. Now, depending on the value of R1 and RF, actually, if you are coming from plus V sub side to minus V sub side, okay, answering to Divanshu and not telling what way I am going, right? You understand hysteresis and all these things, right? You know about this, right? Where have you studied IC160? Okay, very good. So let's assume that I am traveling from minus V sub to plus V sub. There is no point in calling infinity, right? So if I am traveling from here, I know that if it is plus V sub, output is also plus V sub, right? So I am coming this way. If I am coming this way, when this goes to minus V sub, by the way, by looking at this equation, it will go down only when it reaches minus R1 by RF times V sub. Other than that, it will keep on going to plus V sub. Yes? Let's draw the real thing, right? And after reaching here, when I start moving, it cannot go this way because it will wait for this threshold. That threshold is this side. So it can take only this path because of the dynamics of this circuit. Right? You must have studied BH curve. You studied? Or it's also known as S curve, right? Magnetic field and all. I don't know.
So in that green text, you have written minus V supply to VPN. It will be TP.
This is correct.
No, sir, only green text, you have written beside the
Green text V in is equal to V.
near the left side, sir.
Hmm.
So you have minus V supply to VPN.
Yeah. I need to keep this one as P. That is what you are saying, huh? You are correcting me, or you are?
I am asking, sir.
Okay. So tell me, what is your question?
So my question is, you are writing in the green text minus V supply to VP. It should be minus V supply to
TN. Yes, yes, you are right. That is what I'm saying.
Yes.
You are right.
Yes.
Because I started with some assumption just to know that whether this system is in positive or negative. Okay, this is also one more thing which I learned after many years. Like I discovered in 4 years that my student could not understand this. I was going with this assumption, and I just found out just 3 days back when I was teaching something to Himanshu that the system is positive or negative feedback. So it's so you have to tell me whether this system is positive feedback or negative feedback. This is very important exercise. So now we are interested in the whole system. We are not interested in one op amp at a time. Look, you can see there are two loops. The bigger loop is the one which I am interested in. From here to here, because V out by V in has to be negative feedback. So can you tell me which feedback this follows? Is it negative or the positive? Of course this one is positive, but we are interested from here to here, it's in positive or negative. How did you find out negative? Okay, not like that. So the thing is, the technique says that if you are okay, I'm making with the small op amp and then we'll go to bigger one. So if I am increasing this, let's say if Vin is increased, output is increased or decreased? Increased, because this is also plus. It's not written but it's hidden plus. If this is increasing, which is coming back, if negative is increasing, what is the output? It's decreasing, by the way, because this is minus and this is plus. It will be 180-degree phase shift. This is what I wanted to teach, Manas. This was your question, right? That there is a difference between input and output. Phase is 180-degree, right? So this minus 180-degree is the phase, and that is what we are making the reference line to find out the phase margin generally, right? So that is how this minus 180-degree came into the picture. So this is minus, then what is the next phase? This is plus. If this is plus, this has to be minus, and so on, right? Right, so it's plus and minus, it's keep on uh, so if this is 1 volt, it will take some time to reach there for 1 volt, maybe like this. So you can see that it's progressively decreasing, or it follows e raised to minus 80, or it follows, or it will tell you that this system is a first order, right? So that was the thing. Now can we apply same theory for a bigger circuit? And can you tell me what is going to happen if this is increasing? This is increasing or decreasing? Increasing. If this is increasing, what is going to happen? Also increasing. If this is increasing, this is decrease. If this is decreasing, this is again increasing. Look, because the phase between minus and plus is minus 180-degree. So this is which kind of feedback? Positive, right? So this will keep on growing. Instead of doing this will happen, right? So oscillations will keep on growing. It will never reach your V in. Hmm. I can do this one. Yeah. If I do this one, it will be negative, right? So, any problem now? Okay. Mm-hmm. Okay, let's make it as it was. Okay, so this was like this. Now, no, this is also increasing. So this side also increasing. Yeah. So this is negative feedback. Sorry. So this will be decreased. Thank you. Right. Right. Everybody agree with this one. Right. So that is how you need to find out, because in like future classes, maybe we'll have something like 7 8 op amps in a circuit, and there is a technique which is not written in your syllabus, but this is a technique very like not very ancient, but maybe uh, it came into the picture after 90s. So that is called admittance matrix method. Through that directly you can write down the equation without using KCL and KVL, but actually it's KCL and KVL at the back. So that technique will be the last part of our course. This is what I thought, right? Okay, so very quickly one more question: input impedance, output impedance, because today's lecture was not about Bode plot. So Okay, so if this is a circuit, what is the input impedance? Was answering Divanshu's question now. What is input impedance? This is input voltage and this is output voltage. Okay. Do you know Thevenin theorem? Okay. So how many doesn't know what is input impedance and output impedance? Others, okay. Okay. Do not feel shy. Look, this is I'm going to teach it and then you'll be expert of that. How many know about Thevenin? Thevenin theorem? Okay. Others they don't. Divya, you don't know about Thevenin. Okay. So yeah. So what Divanshu is discussing. So what is Thevenin? Look, let's go one by one thing. So Thevenin theorem says that I want to find out the equivalent resistance at particular node. If that node is input and whatever resistance I am finding out, I am going to declare that one as input impedance. If I am looking at output, that node will be declared as output impedance. If I am looking at any other node, still it's impedance, but looking into the system, right? This is one definition. Is it clear to you? Okay. When we are doing the Thevenin, what Thevenin says that I am going to apply here some known voltage. Let's call this one as VTH, and I am going to measure what is the Thevenin equivalent current, and this ratio of these two is going to give me RTH. Actually, I am going to call that one as input resistance or the input impedance, right? This is one thing. But while doing this, we have to remember two things. All the independent sources. Do you understand independent sources? Right? Their value will never change. If you are connecting it, its hardcore value which will never change. Means this circuit when I'm not finding out this input and output impedance, generally I am going to give something like this. So this is independent source. It's not depending on the circuit, it's independent source. And maybe function generator, power supply, all these things, all the independent sources, if they are voltage, you are going to make them open or short. Open or short, Ashwarya? Short. Why short? They have to be open. Okay. Okay. If there is any confusion, okay, and all the independent current sources has to be short. We are not following Norton Thevenin, Mahima, Mahima. Okay. So in Thevenin, which is following the, like, he likes voltage control voltage source, and that's why he is trying to find out everything in terms of voltages, not in currents. So what he's saying, all the independent voltage sources, let's make them open, right? So if there is a circuit which looks like this one, not like this one. So if I want to find out impedance here, I am going to keep these two sources open, so they will not be there for this analysis. And I'm going to do one thing. I'm going to apply a known Thevenin voltage here, and I'm going to find out the current. VTH by ITH will give me the impedance looking into this system, right? This is for finding out the input side, but this was true for independent sources, for open and all these things. But what we need to do for V out, it has to be open, right? Okay, there is one mistake I should say. Yeah, I went in different way. Yeah, Baima, what you are saying, or you are confused, right? Can you tell me Thevenin one more time? I made mistake. Yes. Mhm. Yeah, that was the correct thing. That's why I asked you. Sorry. Short circuit the voltage, independent voltage sources, independent, right? Not. And open circuit all the independent current sources. Okay. And output is always, if it is voltage, it's open, right? And the current is reverse. Okay. So if you know this theorem, we are going to apply it and we are going to find out the input impedance. So what is the input impedance in this system? Can you see, like, inductor and capacitor in series? So input impedance is nothing but j omega l plus 1 by j omega c, right? In Laplace, if you want to write down in Laplace, right? So this is the input impedance, no problem, right? Now I want to find out output impedance. VTH. VTH, the voltage which I was giving there. So I removed that. When I'm doing this, I need to remove the input voltage, right? You cannot short circuit it, otherwise your voltage is already zero. So okay, if there are two sources like this, then you are going to short this one. Yeah, where you want to see the impedance, you are going to remove that and you are going to add one known Thevenin voltage, then it will work, right? So here I removed the input voltage and I connected the known Thevenin voltage. When I am looking at the current path, there are two elements which are coming in series, so j omega l plus 1 by j omega c. What I Yes, yes, Thevenin voltage, yes, correct. Now I want to find out the output impedance. Can you apply same theorem and can tell me what is going to happen here? So all the independent voltage sources, so this was independent voltage source, short, and I'm looking from here, I'm applying the known Thevenin voltage and finding out ITH. So what is the output impedance? Parallel. So you can see that input and output impedances are not exactly same, they are different. That is what you are asking me, that most of the systems should have input and output impedance same, but that's the wrong assumption. We are going to have one experiment on this just to understand, like, this experiment I gave it to long back to students when they are doing IC161 with me. And the first thing was, like, when they were connecting function generator, so I designed such a way that function generator and DSO. So here it was 1 volt with some frequency, let's say 1 kilohertz. I was seeing 1 volt 1 kilohertz. Just look at this, this is function generator and oscilloscope, there is nothing else, right? But when I was connecting this with this one, my output was 0 volt and 1. Yeah, there is no point in writing frequency, right? Or maybe some fluctuations near 1 kilohertz. So all were complaining, sir, our instruments, they do not work. But it's wrong thing. What do you think? What is happening here? So if I remove this, it's all good. If I connect it, there is a problem. What could be the problem? If you want, like, we will do this, right, in the lab, and then I'll explain you, right? You can think about it. This was a question for your batch, right? So this was our quiz one for IC161. It was one question. They have to find out what are the problems here. Okay. So you can think about it. What could be the reason? We are studying something, right? From last 1 hour, we are talking about buffer, we are talking about many things. And that conclusion says that every box will have input impedance and output impedance. You are going to connect something which has lower impedance, it will load, and your voltage will be different than what you are expecting. If this whole thing is equal to 50 ohm, what voltage you are going to get? Half. But if it is not 50 ohm, if it is 1 or 2 ohm, no voltage. So I designed such a way that the value of the inductor and capacitor I am going to give you for 1 kilohertz. Let's say for, just you keep it here. If 1 kilohertz and inductor is 1 millihenry, what is the resistance offered by inductor? 1 ohm, just 1 ohm. What about capacitor? If it is 100 microfarad, actually it's not 6.20 ohm, 2 pi f. So what about this one? So 1 by j omega means j 2 pi f times c, 1 by 2 times pi times 1 kilo times 100 micro, right? So I designed it such a way that for a given particular frequency, the whole thing was something like 6 7 ohm. I don't remember how. So I followed this thing. So if it is much lower than 50 ohm, what voltage you are going to expect here? 0 volt, right? Because it's loading, because the input is not voltage, input is current, because this is current controlled voltage source, right? Now you're following this, right? All good till now. Okay, and we'll again talk about little bit of phase maybe on Thursday, and then we will sign up for Bode plot. Is there any problem in Bode plot, like drawing Bode plot? Okay, just one correction in your assignment. There were 5 questions. So question 1, question 2, question 3. So question 2 says that uh, draw Bode plot for using MATLAB commands, MATLAB command for all 5, and then Simulink for all 5. But instead of this, I thought let's make it first 3 with MATLAB command and rest 2 with Simulink, because the answer will be same, right? So taking printouts is not a good option. Is it possible to keep everything in a single, like one page, right? All these printouts, one page, right? Plots. Yeah, yeah, it will be small. We can read it, right? So rather than having one plot on one page, let's keep, or maybe two side at the most, right? Okay. Any other question, Khyati? Okay.